In the last video, I was talking about the Lagrange points. Of course, the satellite SOHO is sitting here at L1, where the gravity of the Earth and the gravity of the Moon cancel each other out. There are actually 5 points, as you can see, one on the other side of the Earth. These are basically points where if you put a satellite at these points, they basically orbit oops, I don't know what I just did. They orbit the they orbit the sun just like the Earth does, and they follow the Earth basically. So we actually have satellites at L2. There's nothing at L3 because that's on the other side of the sun. And then L4, which I think I was talking about last time, and L5 are 60 degrees, so that's this angle right here, 60 degrees in front of the Earth. If you drew a line from the sun to the Earth, the angle would be 60 degrees, and so that's where L4 is, and then L5 is 60 degrees behind the Earth. And again, these things orbit let me think about it. L4 and L5, I think, are like some of them. I don't remember if those are the ones, but some of them are not very stable. So that you really don't want to put a satellite there. All right. Anyhow, that is. Whoops! Didn't mean to do that. Pause this and go back to the PowerPoint. All right. So this is what got us a little off track here, talking about the Lagrange points. But it's certainly an important thing to know about that. Remember, we're focusing in on the sun. A great deal of information has come from SOHO, and this is what the acronym stands for: Solar and Heliospheric Observatory. That's basically what it comes to. And it's observed all sorts of things about the sun. A lot of the information that we've detected comes from that particular satellite, because the satellite just sits there and watches the sun all the time, and has been doing so for a long, long time. All right, so here it tells you the different instruments. It looks at the magnetic field on the sun. It looks at the solar corona. And then to look at the corona, by the way, you have to block out the photosphere, the actual surface of the sun, and it does that by artificially creating an eclipse. Right? We can see the solar corona when there is an eclipse, a solar eclipse when the moon passes in front of the sun, and you can see the solar corona. We can actually see the essentially sound waves crossing the surface of the sun, and we can also see, of course, ultraviolet emissions and eruptions, which are sometimes called solar flares, sometimes called solar prominences. All right, let's move on. All right, so this is looking at the sun. What elements do we find? And we notice we find most of the elements on the periodic table. The ones that are naturally occurring, by the way, basically all the way up to element 92, which is uranium. So there's really only 92 naturally occurring elements. There are elements beyond 92, but they don't naturally occur in nature. Humans have engineered those elements that are higher than element 92. Anyhow, notice we find most of them, and of course we use spectral analysis. Right? That's the information that we got from chapter 4, what we studied in chapter 4. All right, so let's see. Spectral lines are formed when light is absorbed before escaping from the sun, and basically from the atmosphere, mostly from the corona. That's how we get information about what the sun is made of, and of course, it's made up of mostly hydrogen, right? I forget what the percentage is. It's around 75%. It's actually just a little bit less than that, and then almost 25% helium, and then just maybe 1% of everything else combined. All right. So this is the showing us the chromosphere, and notice the chromosphere is a little bit cooler than the photosphere, right? Remember, the photosphere is sitting at about 5,800 Kelvin. Okay, so the chromosphere is just above this is the lowest part of the atmosphere of the sun. Remember, this photosphere is the actual surface. And as it says here, it's very hard to see the chromosphere. And so what we have to do, or what we used to have to do, is we look during eclipses, solar eclipses. So astronomers used to cross the globe and set up their telescopes to witness one of these eclipses, a solar eclipse, which is a fairly rare event. You have to be right in the path of totality. And the moon gets closer, a little closer and a little further from the Earth, right? That's because it's in what's called an elliptical orbit. Anyhow, when the moon is a little bit too well, either way, a little too far from the Earth, then you get too much of the chromosphere blocked. If it's too close, you pick up too much of the photosphere, and then you can't see. Either way, you can't see the chromosphere. So it's only when the moon is just in the right position and there's a solar eclipse, right, for the moon to be right in the right position for you to be able to see the chromosphere, which is actually pretty rare. So nowadays, of course, we use SOHO, this satellite that can artificially create eclipses. It basically blocks out the photosphere and allows us to analyze the chromosphere and, of course, the solar corona. Here's some stuff that happens within the chromosphere. These are called spicules. These are just, like it says here, just little tiny storms. Nothing like a solar flare or a solar prominence, which extend out beyond the chromosphere and into these giant eruptions can extend out like millions and millions of miles above the surface of the sun. All right, so this is, of course, looking at the solar corona, which is this is this hazy looking part of the sun. This is the outer atmosphere of the sun, and of course, we're still studying the solar corona because there's a property of it that is very, very odd, and you can see that here. Okay, so let's look at this graph a little bit more carefully. Right at the surface of the sun, so this is at zero distance from the surface of the sun. The temperature of the sun is about 5,800 Kelvin, and then in the chromosphere it drops down a little bit. It gets a little cooler, as you can see right here, around 4,500. So it's getting a little bit cooler, and this is all in Kelvin. And then when you leave this lower atmosphere into the upper atmosphere, which is called the solar corona, notice the temperature goes up, and it goes up enormously, and it gets higher and higher. And this was really a big mystery, and it's still a bit of a mystery to us. Why is it that the the upper atmosphere of the sun gets much hotter than the surface. And notice it's at more than 5,000 kilometers above the surface of the sun, the corona reaches over 1,000,000 Kelvin, as it's indicated right here. So why is that? What exactly is going on when you get into the corona? All right. So, and I'll just go into this briefly. We think it has to do with magnetism. Basically, the magnetism is oscillating vibrating the molecules or the atoms in the solar corona. All right, and we'll see how that's done, or how we think that's done. There's actually I mentioned this earlier in one of the earlier videos. There is a satellite that is called the Parker Solar Probe, and it is investigating that. All right, this starts us into studying the magnetic field of the sun, which actually has a lot to do with this temperature thing. The increased temperature in the solar corona. It might not seem obvious, but it does, and we'll explore that in just a little bit. But we got to explain what it is now. So we know, and even during Galileo's time, right? So this is 400 years ago. Galileo noticed, and this was really a bad thing for Galileo to do, by the way. He used his telescope when the sun was just about to set. He looked at the surface of the sun. Again, a really bad idea without a proper solar filter, which of course he didn't have. And then sometimes he would look at the sun right at sunrise as well, and he noticed these dark spots on the sun. By the way, as a side note, poor Galileo, in the last 10 years of his life, was completely blind. He had lost his eyesight, and we think it had a lot to do with the fact that he observed the sun with a telescope, which is just absolutely a terrible idea. All right, but anyhow, so he noticed these dark spots on the surface of the sun, and for a long time these were a mystery, and we began to understand them a little bit around the turn of the 20th century, and we've been studying them ever since Galileo discovered them. And it turns out that these regions are a little bit cooler than the surface of the sun. And they're usually cooler by, a few thousand Kelvin. So, I know I've said this many times now, the photosphere, the actual surface of the sun, is at 5,800 Kelvin. Sometimes you read in books that it's 6,000 Kelvin. I might even say that in class sometimes, that the surface of the sun is 6,000 Kelvin. These dark spots are a little bit cooler, and that's why they appear dark. If you were to just they're extremely bright. The reason that they appear dark is because the surrounding area is putting out more photons than these dark areas. If you were to actually just take one of these dark areas and put it in the night sky, it would be almost as bright as the sun. All right, so these are extremely bright, but the only reason they appear dark is because they're a little bit cooler than the surrounding area, the actual surface of the sun. I mean, these are on the surface of the sun as well, but we'll see that there's magnetic fields underneath that are blocking some of the photons from escaping in these areas, and that's really why they're dark and why they're cooler. All right. So let's look at the magnetism and where the sunspots go. And by the way, this is So when we go back in history, we notice that there were certain years that